Chapter 15, Part 2. In a certain city, 45% of registered voters are Republican, 40% are Democrat, and the rest are independents. Also, 40% of the Republicans are women, 55% of the Democrats are women, and 60% of the independents are women. So we've learned to make tables, but we can also make a tree diagram to help us display the information and answer questions. So we're going to start with the first three things that they gave us was that we have Republicans, Democrats, and independents. And if I look, the probability of being a Republican is 45%. The probability of being a Democrat is 40%. And the probability of being an independent is the rest. Well, 45 plus 40 is 85, so we have 15% chance of being independent. And then we break each chunk down. It says if you are a Republican, 40% of those are women. So 0.4 for women, which would leave, of course, 0.6 for men. Go ahead and fill in the chart, and I will as well. So you should have been able to fill in the chart, again, using the given information they gave you. So we know that 55% of the Democrats are women, so this is the Democrat branch of the tree. And then we break that down into 55% women, 45% men. Now we can use this tree diagram to help us answer the questions below. For example, what is the probability that you choose a person who is Republican and a woman? So that's the probability of Republican and, or the other way to think about it is intersect women. And you're just going to go down the branch. The probability of being a Republican was 0.45. And then if you're Republican, you're Republican and you're a woman, then that's 0.4. So we follow down the tree using our rule of multiplication. 0.45 times 0.4, and you have an 18% chance of being both Republican and women. What is the probability that you choose a person who is a woman? So you have all of these people, and you randomly pick one. Well, we need the probability that somebody is a woman. Well, there are three ways to be a woman in this situation, right? You're a Republican woman, or you're a Democratic woman, or you're an independent woman. So we're going to have to add up three separate probabilities. Well, we already know that being a Republican and a woman is 0.18, but plus you could be a Democrat and a woman, so 0.4 times 0.55, or 40 times 55%, plus you could be an independent and a woman. So the probability of independent is 0.15. Go ahead and times that or multiply that by the probability of being independent, which is, or being a woman and independent, which is 0.6, and simplify that and you get 49% chance of being a woman in this population. Okay, it says, what is the probability that you choose a person who is male or an independent? Well, now we're doing the or, so we're actually going to go all the way back up here and use our or formula, where we're going to add the two separate probabilities and subtract the overlap. So let's do that. So probability of being a male, well, we can figure that out the same way we did before, which would be to add up all the little branches. But if we know the probability of being a woman is 49%, and the probability of being a male is its complement, so that's 51%, plus the probability of being an independent, which we know is 15%, and then we need to minus the overlap, which is the probability of being an independent male. And it'll give us 60%. This is a skill you need to master, so make sure you understand what I'm doing here. Then the last part is, what is the probability that a randomly chosen male is a Republican? So now we're going to remember that this would be both probability of Republican and male, given our formula, all over just the probability of being male. Well, we already know that the probability of being male is 51%. We figured that out using the complement from the probability of being female, so that is 0.51. And the probability of being Republican and male, again, we can just go down the tree, Republican, but this time and male. That's 0.45 times 0.6. and you're going to end up with a probability of 53%, or 0.53, and that is the probability of randomly picking a male, or excuse me, a probability of randomly getting a Republican, assuming that the people you're picking from are males. Okay, and now it says, are being a woman and being a Democrat independent? If they're independent, the probability of a woman has no relationship to the probability of being a Democrat. So in this case, the answer is no, because if they were independent, then the probability of being a woman given you're a Democrat would be the exact same as just the probability of being a woman. But the probability of woman given Democrat is 0.55, while just the probability of being a woman out of this whole population is 0.49. It is possible to use a table to solve this problem, but it takes more work because you not only have to construct the tree diagram or the thinking of the tree diagram, then you use its pieces to construct the table. For example, in this table, if we've got Republican and male, you would go down the tree and go, okay, I'm going to delete some of these highlights I already had here. Let's try this with orange. You'd go down the tree and go, okay, the probability of being Republican and male is 0.45 times 0.6, and you'd have to do that. Right, this is the probability of male and Republican, and you'd get 0.27. Probability of being Republican and female, again, you just go down the tree, Republican and a woman or female, and that's 0.18. We figured it out before. I would like you to finish this table using the tree above. And here's kind of a brief rule of thumb using tables and trees. In general, if you are given counts, then a table or a Venn diagram is easier to use. But if you are given actual conditional probabilities, then a tree diagram is better, so you should memorize that idea. Okay, here's one last example. In a survey of 1,200 college students, 380 said they had tried smoking, 800 had tried drinking, and 315 had tried both. Make a two-way table to display this information. So it looks like what we've done here is we have defined the variables S equals smoking. So obviously S complement is no smoking. Similarly, D equals drinking, and D complement equals no drinking. And remember, AP makes you define all variables. And then they used this data to fill in the table, which you should have been able to do. Now we're going to answer the questions. What is the probability that a randomly chosen respondent has tried neither? Once they said randomly chosen, we know that our denominator is the full amount, so 1,200. And don't smoke, don't drink, that's 335. What is the probability that a randomly chosen drinker has also tried smoking? Well, now we have a given because we know that the person was a drinker, so that becomes my denominator or my given. So how many people drink? Let's clear this table off and look. We have 800 drinkers. And of those 800 drinkers, how many also smoke? 315. Okay, so if you don't drink and smoke, okay, probability of let's see, and then this one is the probability of not drinking given that you smoke. So there are 380 smokers, and of the 380, 65 don't drink. Now we're talking the OR. This would be that long formula again, the addition formula, where we'd want the probability of drinking plus the probability of smoking minus the probability of doing both. So we subtract out the one thing that we've counted twice. And if we look at that, probability of drinking is 315 out of, excuse me one moment. Probability of drinking is 800 out of 1,200. I'll put them underneath. Probability of smoking is 380 out of 1,200. minus the overlap, 315 out of 1200, and we get a total probability of 865 out of 1200. Okay, now a couple of questions. Is smoking independent of drinking? No. If they're independent, again, the probability of smoking giving drinking would be the same as just the probability of smoking, because the fact that you drink would have no influence on the fact that you might also smoke. We know that that's not true, because let's say you are a drinker, you may be also more open to smoking and doing those type of things, and vice versa. It's just the culture around smoking and drinking. If you were to go out with a bunch of people that do that, you might end up doing both behaviors. So the probabilities are a little different. And then, are smoking and drinking disjoint events? Again, the answer is no, because there would have to be no overlap. We could have no smokers that drink and no drinkers that smoke. But since the probability of smoking and drinking is 315 out of the 1200 people they looked at, then they are not disjoint. It would have needed to be 0. And on the upcoming tests, you absolutely need to know how to do these two things, as well as use the addition formula and the conditional probability formula from the table, or finding a conditional probability from the formula or the table. You need to do 31 to 43 before class, and the rest we'll work on in class. I would say just kind of look at the homework and get started so you can come with questions. Thank you.